Good morning,
Good,
Tobias.
good,
Can you hear me?
good morning. Please, you can take it over and proceed.
What is the time? What is the timeline? What is the lineup of things today? I missed your.
According to the program, you have 1 hour. I don't know if 1 hour
Yes.
will be sufficient from now to 10. Then thereafter, at 10:10, we were planning to take some photo because during that time we are supposed to do some evaluation. So the evaluation form will also be up and running on the Canvas platform, so that we can fill it, and thereafter at 12:30 we'll have the graduation.
Okay, I will need just some 45 to 50 minutes. That's all for today.
Okay, no problem.
Thanks.
Okay, thank you, and I wish everybody all the best.
Yeah, thanks. Good morning, friends.
Good morning, Prof.
Good morning, Prof.
Good morning, Prof.
Thank you. On the last lap. Let us wait our friends for the next 5 to 10 minutes. And today I think it's a bit relaxed so that I will tell you a bit of stories related to the analysis of repeated observation, test day models, and things like that. So to get excited or to get bored for the next course, I'll be back in a couple of minutes, 5 minutes or 10 minutes. Let us see how many people are tuning in still. you very much. I think we better start so that we can have a couple of minutes time at the end for some questions and discussions. Good morning again to everybody who have tuned in, and it is very nice to see you all again tuned into this session. So the lineup of my things, what I'm going to do today is, as you might all know, you usually get my lecture notes ahead of the lectures, but this time the topic that we are covering is a very, very, very vast area. This deals with how to deal with repeated observations in animal breeding and the modeling aspect. So I started to prepare something, but last night, it is actually difficult where to start because this has got a lot of different aspects, starting from the basic concept to how the statistical basis and things like that. So I decided that it would be better in a couple of slides to show you what is the story behind the principles, and then show you some practical examples. And finally, I will take you back to the practical aspect, is how we can use the softwares that you have been given access to, like DMU Mix 99. How can you use these tools to build and solve this kind of models, which deals with repeated observations over time, longitudinal data, which animal breeders are mostly faced with. So without further ado, I'll just go directly here. As you might all know, we animal breeders are faced with several different kind of observations measured on animals. For example, we measure egg production in chicken across different laying periods, growth of chicken, fish, or milk production in dairy cows. So these all things which are measured across a time trajectory, they are repeated observations, and we call them longitudinal observations or longitudinal traits. So as you can see here, the fish from the time it is coming to life until it is used for whatever purpose, until it reaches adult, there is a growth trajectory. So at different periods of time, fish growers or fish farmers, they take measurements. These are repeated measurements across time. If you go to beef cattle or sheep, there is also from the day they are born, there is growth process going on at different stages of the life of the animals. We get observations. These observations across a time trajectory are longitudinal data. And the same with chicken. But also there are some observations that are discontinuous or a binary nature. For example, healthy and disease, difficult calving, scaling or categorizing in different categories. One is less difficult calving, 2 is, and 5 is very difficult calving, and things like that. So we have different kinds of observations that we collect from the animals. But going back into these repeated observations which we measure on animals, in the past, the assumption was, and the statistical methods used assume, that although these observations are repeated over time in the life of the animal and measured, we pulled them together and assume them as one observation for that animal during that period of time. I will come back to a very good example of milk production in this case. So when we pulled these observations taken at different times, so at different periods. So what we are actually is, what we are assuming is the animal or the effect or the environmental effect on those observations is as one that is, we assume, a single effect, although there are short-term environmental effects which, if we will be able to correct, that gives us the actual or the correct estimate of the genetic variances or the genetic merit. So in this case, what we know is what is important is even if observations traits are observed at different times, what there is actually a correlation, a kind of correlation, be it environmental or genetic, between these observations. And in statistical inference, accounting this information, covariances between these environmental genetic across the time trajectory is one of the most important aspects. And it is that is why that these covariance functions and on taking the correlation structure within repeated observations is a very important in statistical inference, especially in the analysis of longitudinal data in animal breeding. So how do you create these covariance functions? So these covariance functions are created by regression of the effects on time covariates. And these time covariates are standardized time covariates that when we regress these effects, they give us a covariance function and to account the correlation between repeated observation across time. And these time covariates could be, there are several kinds of time covariates, such as, for example, legendary polynomials, linear splines, B-splines, whatever. You can choose whatever suits to your purpose. And in most cases, especially for dairy cattle and things like that, we use legendary polynomials. And as you can see here, a milk yield observation across time. At the beginning, it is a little high, then goes as a cow dries off and things like that. So if you have not ever seen covariance functions, there is a time index, or for example, here for dairy cattle data, this is days from day 4 until day 365, and the covariables for intercept, linear, quadratic, cubic, quartic, and also a Wilming term here. These are a simple example of a time covariance legendary. There are formulas how to calculate this time covariance, which you can yourself calculate, or you can use an already calculated time covariate functions for use in your analysis. So from studies that we did some time ago, I think it is somewhere in 2008, we analyzed test day somatic cell score data in dairy cattle here in Finland. This is one of the papers which I published on that one. So in this one, before this time, I think before 1990s, especially in dairy cattle, the assumption was there are two kinds of, there was a lactation average model. The lactation average model, as you know, that in milk yield, from the time the calf's born, the cow milks until it is dried off. This it takes on standard lactation, it is about 305 days. But in most tropical environments where we have a situation called short lactation lengths, it may be 200, 280 days. So during this time, before 1990s, what the available statistical method for analyzing this repeated observation across time, like milk yield, and the other, it was lactation average model. By lactation average, what we used to do was we sum up all the milk yields during that period expressed as one observation. For example, during the lactation for Kenana cattle in Sudan or some other breeds, Fogara cattle in Ethiopia could be about 1,000 liters per year. So the observation you have is one. So for that one, we fit only a herd year effect. That is one effect. So when we do that, the assumption is that we don't take account the short-term environmental effects, that we assume all effects there is one effect affecting the whole observation, a year effect or the seasonal effect affecting the whole observation during that time, because you have only one observation. But then after, because this has disadvantages, that you pull down all the effects together, all the observation together, and you don't take account the short-term environmental effects. But in test day models, we have repeated observations as they are. It's not only one observation like lactation average model, but we have every month milk yield. So along with that one, we have also herd test day effects. These are short-term environmental effects that takes account the effect, environmental effect that the animal experiences during that measurement. And by using test day model, we account precisely for short-term environmental effects. And also, it allows us, it doesn't, because in lactation average case, we have to wait until the end of the lactation to get that one observation. But in test day models, even if you have 2 months or 2 test day observations or 1 test day, the animal still can get breeding value for that one. So these are the advantages of this test day model, taking into account the correlations, the covariance structure between repeated observation. But the disadvantage in terms of in this test day assumption or using longitudinal models is compared to the lactation average models is that you may have a lot of observations, or you have to, for example, if you are getting your test day milk recorded every month, then you have about 12 observations per animal. If it is more frequent, that one, and this has some computational and disk space issues, but currently because of the advance of statistical and computational issues, there is no worry to handle these kind of observations. So in this study, what we did was we fit 2 different models. So this was somatic cell, test day somatic cell score observations across lactations, and we compared 2 models. The first one was a fixed regression model, and the other was a random regression model. So in the fixed regression model, which we commonly call a repeatability model, the assumption is that each individual, the observations are repeated observation of the same trait. But in the random regression case, each observation is as a trait. We consider it as a trait. If it is, for example, milk is observed during 305 days, and each of these days are different observations. And in case of a fixed regression model, what we fit is a fixed lactation curve that is a curve for all animals in the population. And also we assume that the permanent effect and the additive genetic effect is the same across all repeated observations for that animal. But in the random regression case, the assumption is over and above the fixed regression that is the lactation curve for all animals in the population, we also assume random variation for additive genetic effect and also the permanent environmental effect, assuming that they are varying across time trajectories. So using this one, with these assumptions, for example, if you estimate your genetic variance, what you get is, here is a curve for the random regression effect, which shows you for each day, the additive genetic effect is different. While for the repeatability model that you get, that the assumption is, we assume the genetic correlation, a correlation of 1, that these are repeated observations of the same trait, so you get the same estimate for the additive genetic variance. And also, the estimate for the permanent environmental variance for the random regression, it varies by day, by each day that you consider in the analysis, while for the repeated observation or for the fixed regression, it is just constant 1 value. And the heritability also, as a function of this, you get a variable across time trajectory for the random regression model, while you get a fixed value for the fixed regressions. So here also what we see is if you estimate your random regression solutions for the random regression model, you can also estimate the daily breeding values for the animal. So here the assumption is that the genes behind for these traits across different traits are not the same. For example, since we saw the genetic correlation between these 300 days between each days vary. So if that varies, we should assume that the breeding value for that animal for each day also varies. I will show you this in short. This is a fixed lactation curve from the analysis. So these are the two different models that we have fit for modeling milk yield. So as you can see here in the fixed regression case, we have a lactation curve, a fixed lactation curve for milk within parity, because this is two-parity analysis, and also a lactation curve within seasons. But here you see we have three random effects, and in this case we assume that these repeated observations are this trait is a repeated observation of the same trait, and we assume the same permanent environment effect across different time trajectories and also the animal genetic effect. But on the contrary, so we get a single heritability estimate for that one. But in the random regression case, since we regress random animal effects and permanent environmental effects on time trajectories, we get a random variance covariance matrix or regression coefficients. And using this regression coefficients, we construct the covariance function that allows us to estimate the correlation between different days and also the heritability across the time trajectory. For example, what you see here is the estimates of genetic parameters for first lactation milk yield using random regression model. So those values across on the diagonals are the heritabilities for this trait, while the below diagonals are the genetic correlations, and above the diagonal is a phenotypic correlation. For example, if you see the correlation between milk yield on day 5 and then on day 100 is 0.97, this automatically tells you that it is less than unity, which means that milk yield at these different days are affected by different sets of genes. And therefore, if we want actually and correctly estimate the genetic merit of that animal, the best model is the one that take into account this genetic variability across the time trajectory. And that's why we are focusing on using those statistical model random regressions to properly and accurately correct for environmental effects and also estimate the actual genetic merit of animals for the different traits. So this one shows your heritability from the random regression model at different days. If it was a fixed regression model, then it's just one line because it's one value. The assumption behind was it is repeated observations of the same trait, but in the random regression, we assume they are different across different time trajectories, genetic values. So here is the estimates of genetic correlation for that data. If you plotted the correlation between day 1, the correlation between day, I think 5 and the day 305 is lower. The correlation between day 5 and day 5 and day 305 or 300 is lower. But as you calculate the correlation between days in milk adjacent to each other, the correlation increases. For example, here you can see the correlation between day 5, maybe 5 and day 30. But as you go here, it is a correlation, for example, between day 5 and 280, it is lower. So this tells you that the correlation between milk yield potential of the animals, genetic merit of milk for milk yield for the animal at different days varies. So the actual model to account that is to take into consideration this variability across time trajectory in these appropriate models. And that's why that mostly we are using random regression model for this evaluation of test state data or observations, repeated observations across time. So with just a very short, brief overview of the analysis of repeated observations across time in animal breeding, I will just take you, how can we use the tools that we have, the softwares, to fit these different models and to get the solutions and to estimate our genetic parameters or to estimate the genetic merits of the animals. With this short overview, if you have questions or comments, I will be happy to. Otherwise, I will go back to my terminal and show you some things.
I have a question.
Go ahead, please.
You mentioned that Legendre polynomials is mostly used in dairy. So I'm just wondering, how do you determine which time covariates to use, considering that I know Legendre polynomials suffers from overestimating, especially at the extremes, because I've dealt with it before in chicken for growth and feed deficiency traits, and I realized it was really overestimating the heritabilities at both extremes. So I'm just wondering, you said Legendre polynomials is most used, but then we know what it suffers from. So how do you determine which one to use?
This is a very, very good question. And if you give me 1 minute, I will show you one paper which I have written sometime in 2008, which deals exactly with this one, which will answer your question very well. Just hold on, I have to find this one. Okay. You raised a very good question, I think. No, it is the same. Just hold on. What's this one? Livestock science. Yeah. Okay, this is a work which we published in 2000. I don't remember now. 2012. Okay, here it's a longitudinal threshold model analysis of clinical mastitis using linear splines. So we compared here two statistical methods because you raised that there are different time covariates that we can use. There are legendary polymers who are mostly used, there are B splines, and there are C splines also, and there are linear splines. And which time covariate to use depends on what you are going to do and the characteristic attributes of these different time covariates. As you have rightly mentioned that legendary polynomials, although they are generally very important statistical tools, they suffer from the disadvantage of giving erratic values at the most extreme values, at the most extreme edges of the time trajectory, especially where in animal breeding we have less observations or high variabilities. For example, at the end of the lactation or at the beginning of the lactation where there is high variability and there are less observations, these covariables, these time covariates tend to suffer or tend to give you some erratic values. And in this study we did, we compared this linear splines with with a legendary polynomials. So as you can see, we estimated heritability for clinical mastitis trait. This is a threshold model analysis. This is whether the animal is diseased or not diseased. It's a binary trait. It's difficult to handle, and the only model that would properly handle that one is a threshold model. But in this case, we use two different time covariates. The one that you see, this is a heritability estimates for clinical mastitis, and this one is from the fitting legendary polynomials, while the other, this is the solid curve. Can you see this paper? Do you follow my?
Yes, bro.
Yes, bro.
Okay, thank you. As you can see, this is a problem that Sophie mentioned. If I use legendary polynomials at the beginning of the lactation where I have less observations, it tends to overestimate my heritabilities. And also at the other extremes, while the linear splice, this solid curve, tend to give me a relatively better, maybe I can make it a little bit bigger for you so that you can see. Yeah, can you see now well? So this is a legendary polynomials. At the beginning of the lactation gave me erratic values. I know they are not that high, the heritabilities, and at this end also. But the solid line, the linear splines gave me a more stable kind of estimate. So in general, my answer to you is it depends on what you are going to do and the characteristics attributes of each of these different time covariates. But it also depends if you have very good data, well-balanced data across the time trajectory, whatever time covariates you use, I think they should give you a pretty good answer or a much more closer answer. Would that answer your question?
Yes, thank you. And thank you for the paper. I think I'll find the paper for more guidance. But thank you.
I can send you by email.
I would appreciate.
Thank you.
Yeah. Hello, Dr. Dr. Anio.
Yes, Jeremias.
Yeah, me also. I would like to thank you for the simplicity with which you have expressed the analysis of longitudinal data, because it directly impacts my work. And I was actually limited in terms of justifying random regression model over repeatability model and also test-day model over lactation model, but you have made it very clear for me. So I will internalize what you have taught us this morning. But I just want to know the covariance or correlation matrix that you have shown us between the time covariates. Are we treating these days as variables? Because as we know in the multivariate analysis, you must have variables for you to establish a correlation matrix or covariance matrix or whatsoever. And now we are trying to find out the correlation between day 1 and day 20, day 25, and day so that we can estimate the genetic effects. So are we treating these days as variables? What are we doing? I just want you to answer some.
Yeah, exactly. That is what it differs from fixed regression. That in the fixed regression, we assume this repeated observation across time trajectory as the same observation at the repeated observation of the same trait. So our assumption is that the genetic correlation between these observations measured at different days or different growth periods are the same, but actually not, because we estimated the genetic correlation between these different days. We see that they are less than 1, as I have shown you in this. Have I closed it? In this one, in this we see that the correlation between day 5 and day 50 or day 150 is 0.64. So this clearly tells you fixed regression model, repeatability model is not the one that properly handle your case, because we know here that these two traits, this every day, as you have said, is a different variable, a different trait in the random regression case. So by doing that, if you estimate the daily breeding for this animal, it is actually different, meaning that the genetic basis, the genetics behind this expression of that trait during that time is slightly different, the one that is expressed at the beginning of the lactation. Or, for example, a very simple example is if you see here, we have negative values. What it actually tells is, I know that is one of the problems of this legendary polynomials at the end of the lactation trajectory that gives you some erratic values. But if you see this 0.01, what it does, this is milk yield trait. So what it tells me is the milk yield at the beginning of the lactation has very less genetic correlation with the milk yield at day 300 or 305. So that means we know that these quantitative traits are affected by many genes. And the set of genes that affected this characteristics performance of milk yield at the beginning of the lactation is slightly different than the one that is at the end of the lactation. So the best way to properly estimate the genetic merit of that animal is by estimating its breeding value for each day of the lactation. So how we can do that is by fitting a random regression model that considers that the genetic merit of the animal across different days in milk varies. Thank you for the nice question, Ermias. And I will quickly show you, if you are interested, just for your interest, how do we fit these models using like Mix99 or using DMU programs in the next couple of minutes. Okay, so here, okay, this one I'm sure. If you have never seen the time covariates, they look like this. It depends. It is legendary polynomials of order 5 or 6. Okay, I should take this one. Okay, now I'm here. I'm opening the DMU directive file. Don't worry, it's a bit complicated, but this is exactly what we started with the day before yesterday when we built the directive file for Univar, for a single trait model. Will you please mute your microphone so that it will take a couple of minutes? Thank you. As you can see, can you see my terminal now?
Yes, sir.
Yes.
Okay, thank you very much. So it's exactly, if you have built the directive file for the univariate model, it is exactly the same. The only thing, as I have indicated in the first day, we started with a univariate model and build up to bivariate model. And what we did when we built the bivariate model is we just added a couple of lines there, a couple of rows. And also when we did the block model for the using DMU, we added just 2 or 3 rows there. So here also in doing a random regression model or a fixed regression model, we just add a couple of lines on the univariate directive file you have created here. As usual, we give some comments and also describe the type of analysis we want to do. If it is variance component estimation, it's 1, and it's also the method depending what you wanted to do. It is either expectation maximization, in which case 2, otherwise it is AI algorithm 1. Then we describe our data here. This is a very big data. We have also these ones until here are the integers, and those below that one are the real variables. I go down. So this is a model section we described. As you remember, that it's exactly the same that as we described it for the univariate model. Here also we tell the program that we have one trait, we don't absorb any of the effects, that we have a 0 there. Then we have a trait line where we describe which trait we are analyzing. In this case, we are analyzing a trait in this column, and 39. It is this trait. And the effects are after 10 years, it's a year effect, it's a season effect, it is a lactation week, we have a permanent environment and animal effect here. So here on the next line, we tell the program which ones are the random and how many random effects we have. We tell here we have 2 random effects. They are 1 and 2. That is the animal additive genetic effect and the permanent environmental effect. So the most important part, especially if you are doing a fixed lactation curve, a fixed regression model or a random regression model, is it is this line. It is a regression line. In the model line, it is a regression line. Here, what I'm telling is, for example, in this model, it is a random regression model where I regress the additive genetic and permanent environmental effects on second order legendary polynomial covariables. So here what I do is, these are how many, this number 4, it tells me how many regression do I have, and the next column tells, for example, which covariable. In this case, it is 50. 50 tells me it is a covariable for linear legendary polynomial, the linear, and within that one I nest effect 5 and effect 6. These are the permanent environment effect 5 and the animal genetic effect number 6. And I take the next covariable, that is 51, which is a quadratic legendary quadratic term, and then I nest the effects within that one. And if I want to fit a cubic, I do the same. So finally, I count how many regressions I have: 1, 2, 3, 4, 5. 1, 2, 3, 4. So it is 4 regression coefficients. When the output is printed, then it gives me, for the permanent environment effect, a 3 by 3 matrix that is including the intercept, the linear, and the quadratic term. And also for the genetic is 3 by 3 matrix that is including the intercept, the linear, and the quadratic term. But in this case, as you can see, I have not specified the intercept term, because I have the intercept term here at 49XO, but DMU assumes, and it fits by default for you, intercept term, so you don't have to specify the intercept term. It assumes. Then it takes the linear and the quadratic terms and it calculates for you. So this is exactly, it is the same line that you use for regressions that does for you to do whether a fixed regression or a random regression model. Then the final part is you give your pedigree, and if you have a starting values, you put a starting value. If you don't have, DMU gives you an identity matrix as a starting value by default, so you don't have to worry about that one. So what do I get? If I run this model, I get something like this. Something like this. So this is, I know this is a second effect, is a permanent environment effect. So this is the intercept. This is a linear, the variance for the linear term, and this is the variance for the quadratic term. And also for the third effect, that is the animal additive genetic effect, the intercept, term, the genetic variance, the random regression coefficient is for the intercept term, for the linear term, and for the quadratic term. So I use these values to construct my covariance function and to estimate my parameters. So you get a para out file like this one. The one I show you is a lower diagonal. This is just indicated by IJ form. So this 2 is a permanent environmental effect, and 3 is the random regression coefficient is for animal genetic effect, and therefore is a residual effect. So how do I estimate the parameters? Then how do get my heritabilities, my genetic correlations? I think that is your question. So I write a Octave is very important. That's why in this course we tried to introduce you to Octave. You can really do very nice mathematical manipulations with Octave. So in this case, I also write an Octave script. It's a little bit, it's not clean and it's not, it's a bit complicated, but I shortly and clearly and briefly explain about this one. What I did was just I read the parout file in. So I have the genetic variance. If you have a herd effect, in some cases, if you have herd-Thursday effect. The second one is your permanent environment effect. The third one is these are the random regression coefficients. So we use these random regression coefficients by multiplying them with the time covariance. We derive our covariance functions, and from that covariance function, we'll be able to estimate our heritability and other genetic parameters. So I read them in, and here I read the time covariance in. I think it is, here I make my covariance function, and there is a place where where I'm calculating my heritabilities and things like that. Here I create, now because my assumption, when I have a covariance function and when I multiply that with the time covariance, I get a matrix for genetic variance covariance matrix, which is a size of 360 or 360 by 360. For permanent environment, the same, and for total phenotypic variance, the same. So this variance is very big because this allows me to take each day as a separate trait. So this will give me heritability. So heritability here I calculate for each day. So I get 365 or 305 heritabilities for each day. And also, if I do genetic correlations here, I get a very big genetic correlation matrix that each day the correlation between different day 1 and day 305 or something. So what do I get from this small script is the estimates of the heritabilities. For example, in this case, if I take this one is heritability, what I did was, instead of printing each day heritability, that means 305 rows, what I did was take place every 30 days, the heritability of the animal every 30 days. So this is a day 1, the day 5, this is a day 35, this is a day 65. This is a very lowly heritable trait, so what you see, the heritability is very low. So what does the genetic correlation like between different days? So I think I have this one. So again, I take this matrix is the biggest, the big matrix is gives me the genetic correlation between each day, that is 305 by 300, but I can index it and extract the correlation between different days. For example, I take for day 5, days 35, 65, 120, something like that. So this will give me, instead of printing a very big file just for having a look, or for publication things, for example, if you want, you cannot publish a 305 by 305 matrix, so you can index it. Because also the second thing is the correlation between adjacent days is very high. than compared to the days apart. So it is better to index it a little bit apart. So in general, in short, this is how you specify, build your random regression model in DMU programs, and also here how you can post-process your estimates of random regression coefficients into covariance function, and finally into your desired genetic parameters, be it heritability, genetic correlation, or phenotypic correlations. I think I can show you the same thing with Mix99. It is the same. Just in short, if you have, I think we have given you a Mix99. One thing we didn't tell you in this course, although you have got the software, is Mix99 is a very versatile program. Apart doing all other things, it can allow you also to estimate variance components. So I think this is a part which we'll cover in the next course, hopefully. So here also, if you have a Mix99 clean, the one that we have used for estimating simple animal models, you can just use that one. You can just specify your model here. You fit, for example, in this case, we fit a fixed curve. That means we have one curve for all animals for all groups of animals during the lactation. But what we did was we nested it with a calving season. So animals calving with a certain season will have a similar or one fixed curve. But here we regress the permanent environment of additive on the time covariate, and here we get the additive genetic effect and the permanent environment effect allowed to vary for each day. So when you run this one, you will get the random regression coefficients for the permanent and environmental for the additive genetic effects. And once you get, in this case, instead of para, what you get is a par file. It is this one. So it's exactly like the one that we saw for DMU. You can read in this file and construct these covariance functions exactly the way I did for my DMU. Here also I did, I wrote a small octave script, and this script reads the parameters and allows me to estimate heritabilities, genetic correlations, and things like that. And I can even estimate, I can show you quickly this one for selected days in milk. This one is the one I have on the diagonals. This is a 300 by 360 matrix. That means I have the heritabilities genetic correlation between each days during the lactation on the diagonal, and the genetic correlation below the diagonal, and the phenotypic correlation above the diagonal. So as I have told you, between close adjacent days, the correlation is very high, so you don't have to publish or print this one. You can just select, index it by at the interval of 30 days or 50 days or whatever. So if you do that, you will get a 13 by 13 matrix, which is showing you that you have heritabilities on the diagonals and the genetic correlation between different days on the off diagonal, and the phenotypic correlation on the above diagonal. So this is in short what you can do with both DMU software and also Mix99 software we provided with you. You have the tools, and just try to run, and if you have some problems, just give us, send an email and ask. We are always ready to help you. If you have quick questions, I can accept some questions or discussions. As we are going, or as we are on the last lap to have your graduation, I think if there are no questions, I would like to thank you all, and it was absolutely an enriching experience to have you all, this wonderful experts tuned in and having fun during the last couple of weeks. And for me, I have done these kind of things at different places and for life, but this one is especially very enriching experience, especially with to deal with and to discuss with our brothers and sisters. Is there is nothing much more enriching and interesting experience than this one. I have enjoyed it really very much, and I really thank you all for your attention, and I wish you a nice graduation.
Thank you.
Thank you, Professor.
Thank you, Prof.
Thank you, bro.
Thank you,
Thank
Prof.
you, Prof.
Thank you very much, bro.
Thank you,
Thank
bro. We
you.
really appreciate you. You really give us
Really appreciate
so many
your
information, so many knowledge, and really appreciate you so very much.
Thank you.
Thank you for taking your time to explain, to do things, making us to understand better. We really appreciate that.
You're welcome.
Thank you, Prof.
Yeah.
Thank you.
I'll definitely replay your presentations and practice with my own data.
Very good.
Yes.
Anytime.
When we get stuck, we'll be calling you, Professor. We have your email.
Yeah, definitely.
You're welcome. I know a lot of I do some traveling. Whenever I happen to be anywhere, then I have people to call on.
Definitely, Prof.
Thank you very much, Prof.
Thanks. You're welcome.
Yeah,
We'll be glad. We'll be glad to host you in Nigeria.
Oh, I would love that.
no, we'll host you in Ukraine.
We are just 400 kilometers away. Thanks, Dr. Keno. Back to you. Is it?
Okay, thanks a lot. And I hope you will stay online for the next few minutes.
Yes,
because
I will.
We have a photo session at 10:10. So I expect more of the faculty members to be in at that time. So that is in the next 8 minutes.
Okay, thanks.
And I would like to thank you so much for taking time to the class.
Yeah, at times it is too heavy, but it is worth sacrificing for brothers and sisters.
Sure, that's true. Thanks a lot. So at exactly 10:10, we'll be taking photos. So please, everybody remember to switch on your camera. If you are to put on your best or your best dress or your best suit, make sure that you put it now. Hi, Victor.
Good morning.
Good morning. How are you doing?
Very well, thank you. That was the most enjoyable lecture.
We just wake up.
That's good. Good to see you.
Thank you very much. Nice to see you.
And you welcome. That was brilliant.
Where are you sitting actually? Now.
I'm sitting in Ilri.
Okay.
I mean. Yeah.
Don't worry, I'm marking your performance here.
Yes, that was I was afraid of.
How are you doing? Well done, that was good. I think they have the students have a double dose of
yes.
So I think they have no excuse now because I'll see you as teaching them as a double dose for them.
You know what I was trying to do was just to excite them so that they will tune in for the next course. So to show them what the horizon, what still we will be able to do in the next course. So I think to get them a little bit excited and also scared at the same time.
They are still listening.
Good, good. So, how is the team? How is Martin and Ismo
It is a very busy time. Actually, I had a very difficult time during these couple of weeks because this is a period where we are writing most of our project proposals, submit and things like that. So we have really tough time.
Okay.
Hopefully, at the end of this month or something, it will get a little bit better.
Okay, that's good.
So how long, Raf, how long will you be around there?
I've been here now this is my 5th week, so I still have around 2 more weeks or so or more.
Okay. So I may be traveling if all goes to Addis over the next 2 weeks, so I can give you a call from Addis, and that's a short distance.
Yes, this is Gabron. Sorry, Tim. Sorry, Prof.
Yes,
go ahead, please.
Yeah, good morning, everyone.
Morning.
Yeah, sorry for, I was out a bit then, I'm sorry for that. But I was with you, Prof. Enyao, this morning. So just 5 minutes, I was out.
Okay.
Yes.
If you need anything, you can ask, or we can send you,
will also be on Canvas in the next.
How long will it be, Dr. Okeno? For how long will it be? The Canvas will be open.
Let me just check with Victor. Then let you know.
There are some lectures we have not yet put in the Canvas and some materials which may help them to do self-study in the future. So we can still upload them there so that if we know exactly how long the Canvas will stay open after today.
Okay, let me just check with the GT.
How is
Okay, it is exactly 10:10. The information in the canvas will be there for some time, so it will not be deactivated soon, as Victor tells me. But that one does not give us a leeway to take all the time before we upload, but it will only be accessible to trainees or the faculty members. But I will encourage the faculty member, the teaching team to make sure that they upload all that have not been uploaded. Because, you know, if we wait for too long, people tend to forget as people engage into other activities. So for now, I'll make a request that we put on our cameras so that we can take a group photo.
How does it work? But okay, if it works.
So Victor, once you are done, you will let us know because we will not know. If you need us to smile, also you will let us know.
Some cameras are not on.
Okay. Can you hear me? Can you hear me? So we can smile. We are taking the photos. So let's see the smiley faces.
Something is coming.
I see some people's cameras are off. I don't know.
Our smiles are expiring now.
Smiles are expiring. That's correct, Professor.
Once done, Victor, you let us know.
It's okay now. We are done.
Okay.
Thank you.
Thanks a lot. So,
can we see the photos?
Thank you.
Yes, you will see them on canvas.
Yeah, you have to share it on canvas.
Yeah, sure.
So the evaluation questionnaire will be activated on the canvas. So I hope everybody will be able to access and then respond to the questions. And then after that, at the same time, there is also the activation of the certificate portal. So you will also fill your name because